like to be treated like children or not be treated. You want to be treated like adults, which I would prefer to do before you come to class. Okay, we were looking at the integral method of analysis. The idea of the integral method of analysis, or any of these method analyses, is to try to determine the rate of the chemical reaction, of the new chemical reaction. What is the integral method analysis? How does it work? What do we do?
We take the data that you have from experiments, and you compare it with, you make a guess of what kind of reaction it is. You integrate the rate.
Educated
An
guess.
educated guess, yeah. And then you take, so you take that expression that you guessed, and you integrate it. And then what you can do is you can create a linear expression, plot that.
I think you're getting too carried away with it. You integrate the equations, and then you figure out a way of comparing what you've integrated with the data. Sometimes you can do it linearly, but not always. So we've done examples where you can come up with linear plots, but that's not always the case. And they would also be considered integral method analysis. So we've done a few examples. We've looked at A goes to products, 2A goes to products. We looked at reactions in parallel. I asked you to look at that. A goes to B and A goes to C. We looked at reactions in series. A goes to B goes to C. All those, and we also looked at A plus R goes to 2R, autocatalytic reactions. Well, all those reactions were irreversible. So what I wanted to do was look at a reversible reaction. So, for example, A goes to R, reversible. So, again, I'm going to assume this is constant density. In which case, 1 over v dNA dt. What do I know about v if I have a constant density? Go back to the second row. Yes? I have constant density. What is this become? Okay, when you say 0 here, what if I ask you your name? You would get that wrong. It's clearly not 0. So you have to remember, when I ask you a question, you're not in front of a 5x squad. When I ask you a question, you have to be able to relax and answer the question. Whether you get it right or wrong, some people get things right, some people get things wrong. But if you freeze up to the point that you want to get your name right, then just imagine you're at your job, and your job depends on your boss's application.
On the reaction, you said this is the one reaction, the three before reaction, the three.
That's the definition. That's the definition. I have not said anything about it. But what you just stated is the definition.
No, I'm asking, as you're going on it forward.
No, I'm answering your question. What you asked is it an equilibrium? I say sometimes maybe, sometimes it's not. I'm giving you general reactions. If I start out with pure A, it depends on the initial condition. If I start out with pure A, literally the rate of the reverse reaction is 0 because there's no R. So they can't be equal. But if I start out with the equilibrium concentration of A and R, they will be equal. All depends on what the concentration is. Okay, so what is this equal to? Remember we have, what's our stoichiometric vector here? Minus 1, 1. And that's why there's a minus 1 here. Okay, so now we would like to solve these equations. Okay, in order to solve it, let's get this in terms of x. So I have what did we call x? What's the name of x? Fraction. So for consequence, we have CA is equal to CA0, 1 minus x, by definition. What is CA0? If I choose it to be the initial concentration, what is sub-zero mean? At the reference state. CA0 is at the reference state. I may choose, I have the ability to choose the initial condition as the reference state. That's not always possible. In this case, I probably will choose it as the initial condition, but it's not necessary. Okay, so this again is CA0 minus CA0 XA. And I can do the same thing for CR. It's CR0, 1 minus XR. Is equal to CR0 minus CR0 XR. Now, of course, what is the physical significance of CA0 minus CA0 XA? Yes, that's exactly right. The amount of A consumed. Since when? Relative to the reference state. And therefore, what is CR0 XR?
The amount of R consumed.
Since the reference state. The reference state may have never existed, but relative to the reference state. So I can relate CA0 XA to CR0 XR by dividing by something. And what I divide by is the stoichiometric coefficient on the right minus that on the left. So for A, the stoichiometric coefficient on the right is 0, and on the left it's 1. So what is 0 minus 1? 1 minus 1. And since that was so easy, we do the same thing for R. 1 minus 0 is 1. And that tells me they differ by minus sign. So this is equal to CR0 plus CA0XA. Because these differ by minus sign. And I can factor out a CA0 times M plus XA, where M is CR0 over CA0. And now I have both CA and CR in terms of X. Well, that's good because I only want one variable. So from here, what is DCA? DCA. In this expression, DCA. In terms of the X.
So I have to
DCA. What is DCA?
CA0,
Almost. What did you leave out? Okay, so DCA dt is minus CA. So now we're plugging into here all these things. So minus CA0 dxa dt is equal to minus K1 CA. CA is CA0, 1 minus XA, plus K2 CR. CR, we said, is CA0 M plus XA. And notice, CA0, all these CA0s cancel. And that's because all the reactions are first order. In first order reactions, in first order reactions, the reference state drops out. Only in first order reactions. Okay, so I have this expression right here, and I can notice that, and let's notice, as was pointed out to us inadvertently before, that since this is a reversible reaction, it, well, actually, before we notice that, let's notice that, remember what our question is. question that we're trying to answer is this a good mechanism for the reaction? That is, does it fit the data? And if so, what are the rate constants, K1 and K2? So one thing we can notice is if we have a reversible reaction, one easy experiment we can do is we just let the reaction sit there until it comes to equilibrium and measure the equilibrium concentrations. That's an easier measurement to make because once you're at equilibrium, things don't change anymore. They just stay there. So at equilibrium, presumably we know the equilibrium concentration of A. So therefore we know XA. And I'm going to call that XAE. So I'm going to let CA equilibrium equal to CA0, 1 minus XAE. So that defines XA equilibrium. And what is the XAET at equilibrium? 0. So one thing I know is that minus K1, 1 minus XAE, plus K2, M plus XAE, is equal to 0. And that gives me a relationship between K1 and K2. So I can determine K2 from here. K2 is equal to K1, 1 minus XAE, over M plus XAE. So I can eliminate K2 from this expression. All right, well, let's rewrite this expression. Got the XA dt is equal to, okay, K2 is equal to K1 times something. So I've got K1, and I can factor out the K1. So it's equal to M plus XA times 1 minus XAE over M plus XAE. I'm taking K2 and I plug it in here. And actually I should have, I changed the sign here, so I should change the sign here. So this has got a minus sign. And then I've got a plus, because I have the minus sign here, so I'm flipping. So this becomes minus and this becomes plus. K1, 1 minus XA. And now I might as well just combine this under a single fraction to make life easier. Notice I factored out the K1 because I've replaced K2 by K1 times something. It's just elementary algebra. Okay, so I've got a K1, and let's put it all into one fraction. So if I put it all into one fraction, I have to multiply and divide by M plus XAE. When I multiply these two out, I've got M minus XA, XAE, M minus XA, XAE, minus MXA, plus XAE. That's the product of this and this, and I subtract this product. So if I subtract this product, I've got M minus XA, XAE, plus XA minus MXA. Yep. Cancel what? Because this is XAE and this is XA. They're different. This is a number and this is a variable. Okay, so let's see what I can cancel here. So I've got M, minus XAE minus XAE. And then these other terms don't cancel. So let's see if I can factor them. So I've got a K1 over M plus XAE. And what am I left with? I'm left with minus MXA plus XAE minus XA plus MXAE. Okay, so it looks like if I factor it, I get an M plus 1 times something. Times, let's see, times XAE minus XA? I'm not sure. Let's just guess. Let's see if that factors right. So I get an MXAE, MXAE with a plus, minus MXA with a minus, plus XAE with a plus, minus XA with a minus. So that factors nicely. And this is dXAE. Well, it was just elementary factoring. And notice the only variable is XA. Everything else is a constant. So I'm going to just put this in at the end. I'll call this capital K. I'll carry it around with me all the time. So I have dxa over xae minus xa is equal to k dt. I integrate this from 0 to t, like the prime there, and this from xa of 0 to xa of t. And this gives me kt is equal to, what's the integral of dx over xae minus xa? Is that 2? Minus the log. So it's the log of xae minus, since the minus the log, I'm going to flip the limits. Actually, I don't have to. So I'll just use the minus xa of t over xae minus xa of 0. Well, what you find here is xae minus xa of t over xae minus xa of 0 is equal to e to the minus, so I'm taking the bring the minus onto the other side, take the exponential, e to the minus, and now I'll plug in for capital K, k1 m plus 1 over m plus xae t. So does this remind you of anything? I have some combination of x's here. It's the distance